In this video, we're going to talk about carbocation rearrangements, and we're also going to talk a little bit about the driving forces behind chemical reactions. In carbocation rearrangements, we have one carbocation rearrange to form another. In this one, you can see that the hydrogen in blue is shifting to a different carbon. But it's not just the hydrogen. It's important to recognize that it's the hydrogen and that bond that it's attached to. So technically, remember when we're drawing electron flow arrows, we can only move electrons. So we're not moving the hydrogen, we're moving the electrons that the hydrogen is attached to. And those electrons are just dragging the hydrogen along with it. So the red carbon-hydrogen bond over here is migrated to form a red carbon-hydrogen bond over here. And that blue hydrogen is just kind of dragged along with the shift. Why does this happen? Well, let's go ahead and identify our carbocation on the left. This left carbocation has 2 carbons attached, so that makes it a secondary carbocation. And on the right, we have a carbocation that has 2, 3 carbon groups attached. So this is a tertiary carbocation. Tertiary carbocations are more stable than secondary carbocations. So this is the driving force behind the reaction. We're going from a less stable secondary carbocation to a more stable tertiary carbocation. And that's why this hydride shift is going to proceed. Let's look at another example. In this example, we have a secondary carbocation, and if you recall, there's a hydrogen attached there. So that carbocation is going to be secondary, and we want to see if it can shift to form a more stable carbocation. Well, where are the hydrogens that can shift? Now, with a carbocation rearrangement, they can't be too far away. They can only be 1 carbon over. So we have to look at the hydrogens here and the hydrogens here. If that red hydrogen moves, we're going to form a tertiary carbocation. But if the blue hydrogens move, that's going to give us a secondary carbocation. We already have a secondary carbocation, and we want to form a more stable carbocation. So this red hydrogen and its electrons are going to shift. So I'm going to draw the arrow, and remember we want to draw the arrow coming from the bond, and it's going to go to that carbon. Let's draw what that gives us. So the red electrons and the red hydrogen that are attached moved over, and our positive charge is now tertiary. So we went from a secondary to a more stable tertiary carbocation. Let's now look at another type of carbocation rearrangement. This is called a 1,2-methyl shift. In the 1,2-methyl shift, we are also going from a less stable to a more stable carbocation, but in this case, it's a methyl group that's getting dragged along with the electrons. Let's follow the electrons here. That red bond that I just drew in is going to move over to that left carbon. And when it does, it's going to form this new bond over here and drag that methyl group along with it. Again, we are going from a secondary carbocation to a more stable tertiary carbocation. This left carbocation is secondary because we have 2 carbon groups attached to it, and the tertiary one has 2, 3 carbon groups attached to it. So again, we're going from a less stable secondary carbocation to a more stable tertiary carbocation. Let's look at another example of a 1,2-methyl shift. So here I have a primary carbocation, It's primary because it's only attached to one other carbon group. And this is going to be pretty unstable. What's going to move is this bond over here that's attached to the methyl group. Let's highlight that in pink here. That bond is going to move over here to the right. And let's draw out what that gives us. So that pink bond came over here, and that means that the positive charge is now in this left carbon over here. So we went from a primary carbocation to a more stable tertiary carbocation. Again, we're going from a less stable to a more stable system. We already started talking a little bit about driving forces for chemical reactions. For example, in carbocation rearrangement, we're going from a less stable to a more stable carbocation. You can also see that charge stabilization in the products is the driving force, as is bond energy in the products. That means that if we can have more stable products in terms of charge or more stable products in terms of bond energy, this is going to encourage a chemical reaction to proceed. In the example shown here, we're going from a negative charge and a positive charge to something that is neutral. So this is what I'm talking about when I say greater charge stabilization in the products. When you have something that has formal charges and you go to something that doesn't have formal charges, that is increased charge stabilization. And so this is a driving force behind your chemical reaction, and this would cause a reaction to occur. This reaction that we're seeing, hopefully you recognize that it's a coordination reaction. So I'll draw on the electrons here as well. We have a lone pair on that bromine that's forming a new bond. The lone pair in the bromine comes into form a bromine-carbon bond. And this is favorable because we are going from something that has charges to something that doesn't. Here are some more examples of driving forces. We have F- over here reacting with HCl. Well, there are actually two reasons why this occurs. One, we are forming a Cl- as opposed to an F-. Remember that chlorine is below fluorine on the periodic table, so it actually handles negative charge better than fluorine, even though fluorine is more electronegative. The size of chlorine is going to help stabilize the negative charge better. Also, we're going from a less stable hydrogen-chlorine bond to a more stable hydrogen-fluorine bond. These two reasons are going to make the reaction occur, and notice we have a pretty big KEQ here, which indicates that this is a favorable reaction and it will occur. Here's another example of a favorable reaction. This one actually has a much bigger KEQ than the one we just talked about, and so this one's definitely going to occur. In this case, even though we're going from an HCl bond to an HN bond, and the HN bond is not as strong as the HCl bond, the big driving force here is the negative charge. A negative charge on a nitrogen is much less stable than a negative charge on a chlorine. You're going from a really strong base and a really strong acid to a weaker base and a weaker acid. So in this case, it's not the bond energy that's the driving force, but rather the negative charge being better accommodated on the Cl- and forming a weak base. So the strong base to the weak base is more important here.